Briefly, we ask the question, by what factors can we geometrically change the length of a given line segment? We've already seen that if we've got a given line segment, we can bisect it, so we get a factor of 1/2. We can bisect it and add that to the length of the original line, the length of the bisect, add half the length of the line to the original. We do that with a compass and a straight edge, and we can get 3/2. We could subdivide the bisecting. We can bisect and bisect again. We get 1/4 the length, and we can add that to the original to get 5/4. We could add it a couple of times, 3 times to the original to get 7/4. We could add it 5 times to the original and get 9/4. So we could just double the original plus original, and add a 1/4. We get 9/4, and so forth. Now, of course, we can also extend the length by factor 2, 3, 4. Just get the length of the line, and then add it, and you got 2, and then add that and get 3, and so forth. And naturally, if we continue bisecting, we can get 1/2. We can bisect 1/2. We get 1/4. We can bisect 1/4. We get 1/8. We can bisect 1/8. We get 1/16 of the original length. ... forever. Now, of course, to do it with real-world instruments wouldn't take all that many bisections, and depending on what size you start, length of line you start with, on the order of about 30 bisections, and you'd be down to the width of an atom, and it'd be really impractical to build a compass smaller than the width of an atom, since you have to build it out of atoms. So you have limits to what you can actually do in the real world, but theoretically there's no limit to how many times you can bisect the line and how tiny an increment you can get. Okay, so can you show now how to build a list of all possible factors? Okay, or at least a list of the possible factors you can get from what we've talked about here. We've already got one list. Actually, we've got 2 parts of the list. 2, 3, 4, ... Those are all possible. 1/2, 1/4, 1/8, 1/16, ... continuing along the same scheme. It's all possible. If we use n for the number of times we want to extend the line, then as long as n's a whole number, this is okay. This would be 1/2 raised to the n power. So all these powers are possible. Now this indicates that n just represents whatever number you want it to represent. It's going to be an integer, positive integer, and 1/2 to the n, you're raising to the power of a positive integer again, and that extends through all positive integers. Okay, all possible positive integer values of n are in this sequence. Okay, so then a question is, can you show how to get a list or multiple lists that would indicate all possible fractions of this nature? That would be a good start. Okay, then we add the related question, or pose a related question: can you trisect a line segment? There's something very advanced in mathematics called Galois theory, and Galois theory can be used to show that no, it's not possible, and to show that other things that mathematicians, the Greeks did incredible things with geometric constructions. They posed this question. They could never figure out a way to do it, and people have ever since, the ancient Greeks, up through about 100 years ago, well, a little over 100 years ago, trying to trisect a line segment, and or trying to prove that it couldn't be done. It took incredibly advanced mathematics to do that. Mathematics that, if you started in your freshman year with a rigorous mathematics course, calculus course, very rigorous calculus course, at an institution that didn't offer anything under calculus, a research institution, and continued on through graduate school, through your work on a research PhD, which is not to be confused with the kind of PhDs you buy from online institutions or from institutions that basically just sell their degrees. The kind of degree you get if the school pays for your graduate school, and you help pay them back by helping with the research and teaching courses. That sort of a school. In your fourth or fifth year, typically, you would get to the point where you could understand this. So I'm not going to explain it to you right now. Come back in about 8 years when you have the background. Of course, I probably won't be able to explain it at that point because I'm getting older. Okay, and mathematicians do decrease in their comprehension, the ability to comprehend things as they get older. Maybe. Come back and see. Okay, so now what about some rational number factor other than one whose denominator is a power of 2? Because we can find that the powers of 2 occur in denominators here in a way that indicates, if you think about it a little bit, well, anything you get on this list is going to have denominators with a power of 2. Now, you might think of other things. There are other numbers. So I originally said yes, I was thinking rational factors, but there are irrational factors, where the answer would be yes, but not rational factors. And I'm 99% sure of this. I'm 199% sure of this. I'd have to reconstruct the Galois theory and prove it myself before I could tell you. But I do know the Galois theory says this, and I think for the same reason, the same field extensions, the same polynomial groups give you answer no for any number that isn't a power of 2. Now, what about a power of pi? Okay, so those are all good questions. You start addressing them by making this list.